Uh, Good evening, everyone. Am I audible to you guys? Okay. If anyone have any doubt, you can ask, like in lecture 1 to 3, week 1 to 3. Otherwise, we can start the session for the week 4. You can unmute yourself, or also you can put your question in chat box if you want. Lead to Portland coastlines and leads to improved liquidity. So for this the answer will be the because the interconnectivity of porosity decreases due to refinement of pore. So what is the doubt in this? Filling of pores. Usually since this is a master level course, so we expect everyone to write in some technical language. That's why the option given filling of pores won't be the correct option. It will be refinement of pores. Filling means you are filling it with some material. However, what is happening, your pores are getting smaller, right? So that's why we won't use the word filling of pores, we will use the word refinement of pores. I hope it's clear. Okay. Any other doubt? Okay, if there are no more doubts, then we will start the session for today. So, good evening everyone. I am Shefali Agarwal and this is our fourth TA session on the topic of advanced concrete technology. In this week, you might have studied about concrete aggregates and chemical introduction to chemical admixtures. So if we talk about concrete aggregates, so first thing is what should be the characteristic of our aggregate to be used in the construction industry. We cannot use any type of aggregate when it comes to using in construction industry. So what should be the different properties of your aggregates and how it should affect the properties of your concrete. So first and foremost thing is prior exposure and processing factors. So its shape, texture, size, and then its porosity, density, and how it is affecting the properties of the concrete. So if it is having more pores, it will absorb more water, water absorption properties, all those things. And then when we are its microstructure, then second thing is its microstructure property. Then it again will contain your porosity, density, and your mineralogical composition like crushing strength, abrasion strength, uh, crushing strength, abrasion strength, elastic modulus, soundness, and lastly about the properties of hardened concrete like ultimate strength, abrasion resistance, dimension stability, and durability. Next thing is when we have any 1 minute. Okay. Other thing is when we have an aggregate in our concrete, there is a area between your aggregate and your concrete, your hydrated concrete or your hydrated paste, which is called as interfacial transition zone. So in this interfacial, if you can see here, in this interfacial transition zone, there is more quantity of attringite and CH or calcium hydroxide as compared to CSH, your calcium silica hydrate. So this zone is called as interfacial transition zone and the remaining part is your bulk cement paste. So what is happening with time? Screen is not showing. Now also it's not showing. Wait. Is it visible now? Okay. So what is happening, if you can see in this case, if this is your aggregates and this is your interfacial transition zone. So since your interfacial transition zone is maximum consist of your ettringite and your calcium hydroxide, what will happen? The density of this area, or the porosity of this area will be very high and your density will be very low. So this can be a weak zone in your concrete system. So if you have continuous or continuous ITZ, what will happen? This will form a, like, if we, 1 minute. So as we are telling that this will be a weak link. So if you have too much aggregate or ITZ is connected, like in this case, so it will form a weak link in your concrete, and your concrete will have more chances of crack along this plane. Okay, so a continuous ITZ is also not good for your durability property of the concrete system. Other thing is, if we talk about concrete strength and flexure strength, so what is happening, if there is a perfect bond, if there is a good bond between your aggregate and your cement base, then you have a very you have a good compressive strength property, and if it is no bond, your strength property will be low. Same way for friction strength or modulus of rupture, your bond, if you have a good bond, your property will be better, and if you don't have a good bond, your property will be very low. Other thing is, what is happening if you are changing your type of aggregates on the different properties of the concrete. So first thing is, what is happening in case of elastic modulus and cube strength. So you can see, if you are using dolomite type of aggregates, you have a very high strength and elastic modulus. However, if you are using very weak type of aggregates like siltstone or granite, your properties will be lower. Same way, other property which your aggregates are affecting in concrete system are shrinkage and creep. So same way, based on different type of aggregates, your shrinkage, relative shrinkage will be different, and same way your relative creep will be different with addition of different type of aggregates. So if we talk about, so this is the effect of your different type of aggregate on shrinkage and creep. So normally in India, these are the 4 different type of stones which we are using as in coarse aggregate in our concrete system: granite, limestone, magnetite and quartzite. Okay, so now we are getting rocks, we are getting stones, aggregates from stones, stones from rocks, and rocks are coming from the minerals. So what should be the basic mineral properties which we look into when we are using that as an aggregate in our concrete? First is color, streak, luster. So these all properties are already given and explained in the class, you can read it through. So these are the few properties which we look into the mineral before using it as an aggregate in our concrete system. So from minerals, the rocks are formed. We have 3 different type of rocks: igneous rock, sedimentary rocks and metamorphic rocks. So igneous rocks are from the molten metal, and your sedimentary rocks are the deposit along the weathered sediments from the river and all, and your metamorphic rocks are the pre-existing rocks subjected to heat and pressure, recrystallization of them. And what should be the properties of this different type of, what are the properties of these different type of rocks, and how they are useful in our concrete system? These are the few points, and there then few example of different type of igneous, metamorphic and sedimentary rocks. Okay, now we have read about what are the different type of aggregates. We know when aggregates come into contact with the concrete, there is a formation of ITZ, interfacial transition zone. But at this interfacial transition zone, there are some problems happening. What are those problems? Mainly we have 2 type of problems. First is alkali silica reaction, second is alkali carbonate reaction. So in alkali silica reaction, what is happening? If your aggregate have reactive silica to it, that reactive silica will react with the alkalis present in the concrete system, your high hydroxide, which will give alkalinity to the concrete system. And when these two are reacting, they are forming a ASR gel, alkali silica ASR gel, alkali silica reaction gel. So this will form alkali silica gel, which absorbs more water from the surrounding paste. And then what is happening, because of absorbing of water, this gel, it will expands. So when it is expanding, it will apply pressure to your concrete system and your cracks will start generating from this point. Okay, so this is one of the problem of interfacial zone of concrete and aggregate. Another problem is alkali carbonate reaction. So what is happening, if you have more carbonate sedimentary rocks, for example in this case we are telling limestone and dolomite, what if they have more carbonates in that, it will again react with the alkalis of your concrete system, and same thing will happen. You will have a alkali carbonate gel forming around the aggregates, and it will exert a pressure onto the surface. And mostly if you see this type of map cracking in concrete, that is a result of alkali carbonate reaction. Okay, however this won't exert that kind of pressure as ASR, and it is limited to few type of aggregates which have sedimentary carbonate present in it. Okay, so this is what is about the aggregates in concrete. If you guys have any doubt, you can ask. Okay, if there are no doubts, then we will go to the second topic. Second topic is on chemical admixture. So what exactly is a chemical admixture? These are the chemicals, liquid chemicals, which we are adding to the concrete to enhance the property of the concrete. So property, how we are enhancing, it can reduce the water content required in the concrete, it can accelerate the reactions, accelerate the hydration or retard the hydration, make it to set fast, set later. So those type of whatever we required, changing the properties of a fresh and hardened concrete, those admixture chemicals which we are adding are called as chemical admixtures. So usually paints and protective coating doesn't include to the admixtures because they are surface applied things, not the things which are mixed into the concrete. And so main type of admixture which we are using in concrete are classified as water reducer, which are reducing the amount of water required for making concrete, set controlling chemicals, accelerator or retarders, those kind of thing. Then air entrainer. So mostly in colder region where we have problem of freeze and thaw, we need some chemicals which can provide some bubbles in the concrete, which help in preventing cracks due to freeze and thaw, that is called as air entrainers. And then some special admixtures like viscosity modifier, corrosion inhibitor, shrinkage reducing, SBR latex and other. Okay, so in week 4 you might have only learned about two type of admixture, water reducer and set controlling chemicals. All other will come in the like week 5, so we will talk about them there. So if we talk about water reducer, we have three type of water reducer: normal, mid-range and high range. It is depending on how much water reduction is happening in these three type of reducers. So if we talk about our super plasticizer, I think everyone is familiar with them, so that they will come under the high range water reducers. Okay, so what is happening? So if this is a curve without a super plasticizer, and this is the curve with super plasticizer. So it is a curve between flow table spread, so flow table test we are doing, flow table spread dimension and water content. So if you increase your water content, your flow table diameter will increase. So without SP, and this is a case with SP. So what is happening in case we have fixed our water spread? Let's say we want only 50 centimeter of water spread. So in this case, without SP, with SP or water cement, your water required will be much lesser than what is without super plasticizer. Same way, if we fix our water content, what we are doing, if you are fixing a water content, your flow will be much higher with super plasticizer as compared to without super plasticizer, right? So what exactly this, 1 minute, what exactly is this table representing here? Is telling at a particular point, if we want to increase the workability or if we want to increase the flow of the strain flow, then this way we are going. And if we want to increase the strength of our system, so what we are doing, we will reduce the water content. Okay, so this is how you will read this table. Other thing is how our super plasticizers are made. So normally super plasticizer are organic molecules, long chain polymer organic molecules. So how this is formed, I hope you all know. So it is a building block made from the monomers. Monomers are the basic organic compound or basic unit cell of organic compound, and when multiple monomers are joined, so we will have a polymer. So if it is joining in a linear way, if it is joining in a branch way or cross linking way, and then these are the different type of how our monomers joins and form different type of polymers. So this is linear, this is branching or cross linking, this is if it encounter any charge, then it is counter ions, charge with counter ions. And then if there are multiple type of monomers connected with each other in chain, cross linking, anything, then they are called as copolymers. Okay, so these are the molecular structure of all the super plasticizer we are using nowadays. Lignosulfate, sulfonated naphthalene, formaldehyde, polycarboxylic ether, and sulfonated melamine formaldehyde. These are the 4 basic type of chemicals which we used as super plasticizer, and this is their basic unit cell or chain, and what should be their molecular weight, and what are the what are the atoms mostly used in this. All those things are given here. And next is the what should be the characteristic of your super plasticizer. So if we talk about bulk super plasticizer, if we talk about only chemical, what we are looking in that, pH, percent solid, viscosity, specific gravity, surface tension, and LOI and TGA. And if we talk about physiochemical properties of your SP, so what will say, what are the elemental things in our SP, what is the acid base titration, charge density, molar mass distribution, and it will be done using NMR, IR, or UV spectroscopy. Last is functional thing. So if we want to see how they are working in our concrete, what we can check, their rheology of the paste with cement paste, the zeta potential on reference minerals, adsorption on various minerals, influence on hydration reaction, and specific interaction in case of a specific type of chemicals if we are using. So if this is your mineral paste, and if you are adding 10% of water, you are getting a good flow value. Same way, if you are not adding extra water but adding a super plasticizer, you are getting a better flow as compared to adding the water. So this diagram actually show the advantages of your addition of super plasticizer in any chemical thing. So next thing is, how exactly are the superplasticizer working? What is the mechanism of action? So as we have talked about 4 different type of superplasticizer. So these are all are old superplasticizer, and currently what we are using is PCE based superplasticizer or poric carboxylic ether based superplasticizer. So all the old superplasticizers main mechanism was electrostatic repulsion. So it was assumed that cement have positively charged ions which attracts the negatively charged ions in the molecular chain, and it will cause a repulsion between different cement particles. So this also have positive charge, so it will cause a electrostatic repulsion between two cement particles, and this is the basic mechanism of action for old type of cement superplasticizer. But if we talk about PC based superplasticizer, polycarboxylic ether, in that case the main mechanism is steric hindrance. So what we are telling that your polymer is getting adsorbed over to the cement particle, and the long chain of your molecule, it is repelling the long chain of another molecules. So there is a hindrance between the molecules, different molecules or different recipe, which is called as steric hindrance. Okay, so next thing is, so this is the mechanism of action of your PC based superplasticizer, and this is the mechanism for your other type of superplasticizer or first and second generation of superplasticizer. So this is what are the influence of structure aspects of PCE. If we have lower dispersibility or shorter dispersibility retention, your relative chain length should be long, and your relative side chain length should be less, and number of side chain length should be more. Same way, if you want higher dispersibility, your chain length of backbone should be short, however your side chain length to have more steric hindrance should be long, and your number of side chains should be small. Same way for long dispersibility retention, it should be short, long, and should be larger. So when now you have added your SP to the concrete, and sometime what is happening, you will have some compatibility issue, and how to check if your superplasticizer is compatible with your mix or not. So incompatibility is defined as the lack of expected level of performance when a given combination of cement and superplasticizer is used. So how we will get to know if your superplasticizer is compatible with your concrete or not? We are doing slump test. If you are getting poor slump retention, or it is causing retardation to the concrete, or there is bleeding or segregation in your concrete, or low early strength. So these are the few performance indicator to check if your superplasticizer is compatible with cement paste or not. So if we talk about PC based superplasticizer and the older superplasticizer, we are telling PC based superplasticizer have lower compatibility issue as compared to your older SNF superplasticizer. Okay, so that's all what you might have studied in week 4. If you guys have any doubt, you can ask, and otherwise we will go to some question and answer for this week. You can put your question in chat box also, or you can just unmute yourself and ask. Rahul, you want to ask any question?
Ma'am, please discuss about the structure of SNF and polycarboxylic ether and lignosulfonate.
So these are the basic molecular structure of your lignosulfate, SNF, SMF, and your PC based inhibitor. Oh, sorry, superplasticizer. So in lignosulfonate you have both calcium and sodium. So if you can see here, this is mostly your ring based benzene based system. So you have a benzene ring which is a long chain of different monomers, right? You have different type of monomers in this case. And same way, if you talk about SNF, here again you have a one monomer, and it have sulfur and your different benzene ring. However, in case of carboxylic acid, you don't have this benzene rings monomer. You mostly have your alkane or alkane based chain. And also it will be mostly what we say, you will have a ketone and what exact the word is, CO is ketone, right? So you will have ketone bond, and mostly it will be I say linear chain. It won't be ring chain. That polymer, the main difference between these two type of superplasticizer is, in this case it is a linear kind of chain with simple molecules. In this case you will have benzene ring which is difficult to break. So it is having it will have charge to it, which will react with the cement charge. It will charge your cement particles, causing a electrostatic repulsion. However, in this case, as we say that it is a linear chain, so what is happening, these CH2, that bond will break, H2 bond will break, and it will adsorb over to your cement particle. And this remaining part, the long chain part, it will be causing the steric hindrance when reacting with the similar type of PCE with similar chain. So they both will be they both won't react with each other. That's why it is called a steric hindrance. Am I able to explain? Is it clear?
Yes.
Okay.
Yes. Okay. Thank you.
Can you explain about steric hindrance once again? So in steric hindrance, what is happening? Your the backbone of your, like, if we see here, so this will be your backbone of your chemical, and this will be the kind of chain, long chain of chemical. So what is happening, this backbone, it will break the bond will be broken, and it will adsorb over to the cement particle. Okay, and this long chain, it will be free in the environment. And again, this is the long chain of one chemical, this is the long chain of another chemical. These two things won't react with each other. And unlike this electrostatic repulsion, since this is a linear change, it won't have any charge to it also. So these long chain, they are not reacting with each other, and so they will be in the air, like they will be in the atmosphere somewhere, and they won't let the other chemical come close, other cement particle come closer to the first cement particle. If this is a first cement, so because of this hindrance, it will stop these two particles to come closer to each other, and that is why it is called as steric hindrance. Am I able to explain?
What, ma'am, long dispersibility tensions, you see the table, and the last relative chain length of backbone polymers shorter, long, and larger. It is the example of PCE.
Yeah, this is the property of the PCE. If you need retention for a longer time, in case you want a longer time retention, so we prefer that your side chain should be longer, and your number of side chain should also be more. Any other doubt?
No, ma'am. Thank you.
Thank you. Okay, so we will see some questions. So first question is, which of the following is not a function of aggregate in concrete? Reducing shrinkage and cracking, providing bulk to the mix, increasing cement consumption or improving density of concrete? Anyone? You can put your supposed option in chat box also. You can mute also. C, increasing
C,
cement
madam, C.
correct. So when we are adding our aggregate to concrete, we are expecting we are reducing the cement consumption, not increasing the cement consumption. Okay. Which property of aggregates affects the bond between cement paste and aggregate? The shape, surface texture, porosity, all of the above.
B.
D, correct.
All.
Correct. So if we have good shape, we will have more surface area. More surface area means more bond, and if you have more surface texture, same way more surface texture will respond to more surface area, causing better bond. And porosity, if you have a little bit porosity into it, your cement particle or cement paste will get attached to it and will have a better bond between cement paste and aggregate. Okay, next question is, what is the primary role of the ITZ in concrete? It controls workability, influences the bond strength and durability, increases water absorption, or reduces thermal cracking. B. Okay. Yeah. So if you remember, we talked about ITZ. I don't know if I have add the figure or not. Yeah. If we talk about ITZ, what is happening at ITZ? It is the part of ITZ will affect your bond strength and the durability. If you remember, we have seen that if there is a long if there is a connectivity of your ITZ, it can cause cracks, which will be a durability property. Next question is, sedimentary rocks such as limestone and dolomite are particularly susceptible to alkali silica reaction, alkali carbonate reaction, thermal. Correct. So this was directly given in the slides. When we are using sedimentary rocks which are having more carbonates, it will cause alkali carbonate reaction. Why are flaky and elongated aggregates generally undesirable in concrete? They increases the cement demand, reduces the abrasion resistance and strength, they improve the durability, or they enhance the workability.
B.
Reduces abrasion resistance, strength. Okay, correct. So in case I hope everyone know what are the flaky and elongated aggregates, and we will do that test with different type of different dimension scale, and then this one to check the flakiness and elongation number of our aggregates. I'm not sure if that is taught in class or not, but you guys should know these two tests which we are doing to test the flakiness and elongation of aggregates in the concrete. Next question is, which of the following is not a typical engineering concern when selecting aggregate rocks? Presence of soluble minerals, cavities in limestone or marble, directional foliation in metamorphic rock, or color of the aggregate? D. Correct. So if we talk about engineering properties, the color of aggregate doesn't matter for us. So these are the main consideration. It is all given in slides, which should be considered when we are selecting an aggregate rock, and it consists all three of these things. So the answer will be D, color of aggregates. Oh, sorry. If the ITZ or interfacial transition zone in concrete becomes highly percolated, what properties most negatively affect? Elastic modulus, shrinkage, durability, or thermoconductivity?
Durability.
Yeah. So we have seen that figure. If you have percolated continent ITZ, there is a chance of cracking along that line, which have the direct effect on the durability of your concrete. Okay. Next question is, if a sedimentary rock aggregate reacts strongly with HCl during testing, it is most likely a quartzite, limestone, basalt or granite.
Limestone.
Limestone. Okay. Anybody else who thinks something else? Okay. So since limestone is the sedimentary rocks having carbonates to it, it will strongly react with the HCl. Okay. Which situation is most likely to trigger alkali carbonate reaction? Concrete. Use of marble aggregates in decorative floor, dolomite limestone aggregates in structure concrete, quartzite aggregates in bridge decks, or basalt aggregates in pavement. Any idea? B. Okay. Anybody else who thinks some other option is correct?
D, madam, D.
D. Basalt aggregates in pavements. Okay. But basalt doesn't have carbonates to it, so we are talking about alkali carbonate reaction. That's why we will say option B is correct, because dolomite limestone will have more carbonates as compared to basalt, and it will create more alkali carbonate reaction issue as compared to your basalt aggregates. Okay. So next question is, aggregates provide dimensional stability to concrete and resist the time dependent deformation. True or false? True. Correct. So that is a direct statement taken from the slide. When we are using aggregates, it will provide a more dimensional stability to your concrete structure. So choose the correct statement. So in between, in this question and answers, I'm going, I think, really fast. So if anybody have any doubt in between also, you can just raise your hand or just unmute yourself and tell. Okay. Choose the correct statement or statements. Cement paste away from the aggregate has more CSH. Paste closer to the aggregate has less CH. Paste closer to aggregate has higher porosity. The failure surface passes through the aggregate in normal strength concrete. What do you think? A and C. Okay. Yeah, correct. A and C are the correct option. So we have seen that ITZ diagram with aggregate and CSH more at this part. So you have more CSH away from the aggregate, and near to the aggregate you have more of ettringite and CH, which will create high porosity near to the aggregate area. Next question is, which of the following is not considered a chemical admixture? Water reducer, corrosion inhibitor, paint coating or air entrainer? C. Correct. Paint coating. At higher dosages, lignosulfonate based normal water reducer may cause excessive acceleration, excessive retardation and bleeding, reduced porosity or higher early strength.
B.
B. Excessive retardation and bleeding. Correct. So next question is, which mechanism explain the action of polycarboxylic ether superplasticizer? Electrostatic repulsion, steric hindrance, adsorption of calcium ions? Correct.
Steric hindrance.
Right. Why are sulfonated naphthalene formaldehyde SNF admixture are sometimes incompatible with certain cement? They react with C2S, they compete with gypsum for C3A site, they crystallizes in pores, they reduces sulfate solubility. B. Yeah, correct. So what is happening? when we are adding SNF type of admixture. If you remember, we have talked about our hydration curve. So what will happen? It will react with the C3A and will then you will have unhydrated gypsum in your concrete system. So that's why what we usually do, if we have to add SNF, we will add it after some time, after initial hydration of your cement paste. So that's why we have delayed addition of SNF in a solution. Which admixture would be more suitable for precast concrete elements in cold weather? Melamine formaldehyde based superplasticizer, naphthalene formaldehyde, PCE based lignosulfate.
A.
Okay. A, C. So if it why the answer is actually A, since we are talking about cold weather and precast concrete elements. So in precast concrete elements, we your formaldehyde, melamine formaldehyde will provide a rapid strength gain and early setting, which are required for the precast concrete. If you are talking about PC based superplasticizer, so PC based superplasticizer are reducing your water content but are not providing your early setting time. It's not as an they are not used as an accelerator. So that's why it's not PC superplasticizer. Okay. A concrete mix with high alkali cement shows poor slump retention when SNF superplasticizer is used. What is the most likely solution? Adding more SNF, delay addition of SNF, replace SNF with melamine formaldehyde, or increase gypsum dosage in cement? Any idea? So we are talking about SNF superplasticizer. I think last to last question also we talked about the same thing. If we are adding SNF super B, correct. So if we are adding SNF superplasticizer, it is fighting with the gypsum for the C3A sites, and it can cause the incompatibility issue in the concrete system or in your concrete cement paste. So what is the best solution is we add SNF after initial hydration or delayed addition of SNF. I hope this is clear with everyone. The typical water reduction range for superplasticizer is 2 to 5%, 10 to 15, 15 to 25, or 30 to 40.
C.
Correct. So superplasticizer are type 3 or class 3 water reducer, high range water reducer with 15 to 25 water reduction. So next question is, which property of cement influences admixture compatibility the most? Your blend fineness, C3A to gypsum ratio, initial setting time, C2S content.
B.
B, correct. So we have been talking about in all the slides that your C3A to gypsum ratio will influence the compatibility. Which test is commonly used in QC to check admixture compatibility? So QC is quality check. Compressive strength test, Marshcon, blend fineness, soundness, Marshcon, correct. So I hope everyone know how Marshcon is done. I think it's in week 5 also, that complete about information on Marshcon test. So you will read about it there. Which molecular feature of SNF is essential for superplasticizer effectiveness? The hydroxyl group in alpha position, sulfonate in beta, carboxylate in gamma, or none of the above? B, correct.
Sulfonate group in beta position.
Correct. So your sulfonate group in beta position is the essential feature for superplasticizer effectiveness. Why is PCE generally more compatible with modern cements than SNF? because it acts by steric hindrance, it absorbs silica only, it reacts with gypsum, or it consumes C3A.
A.
Yeah. So your steric hindrance is much more stable superplasticizer mechanism as compared to your electrostatic repulsion. That's why we are saying PC based superplasticizer are more compatible than SNF based. Which admixture system often requires modification for consistent performance? Lignosulfonates, SNF, melamine, or PCE? A.
Lignosulfate.
Correct. So if in case of if you add more sugar, there are chances of retardation. So therefore you need modification when you are adding your lignosulfate to adjust your acceleration retardation or the property you need. A ready mix truck is delayed for 2 hours in hot weather. Which admixture do you think would be the best help to maintain the workability of your mixture? Retarder, PC superplasticizer, melamine, PC. Correct. So the last question is high dosage of retarders may cause early stiffening, setting delay and strength loss, heat of hydration, or air entrainment.
B. B.
So B is the correct option. So that's all for this week 4, and I'm really thankful to all of you to have this interactive class and replying to questions now and then. If you guys have any doubts, you can unmute yourself and ask.
Madam, in Jota potential process, cement grain have only positive charge or negative charge. Can you explain?
In zeta potential, we say that
In Jota potential.
In zeta potential,
in Jota potential, cement grain. Madam.
In zeta potential, what we are telling, your cement grain will have positive charge.
Yeah, negative charge.
Positive charge. It's mostly positive charge. And your SP will have a negatively charged. So two cement grain with positive charge, they will repel each other. Where can we get links? I will upload all the links today. I forgot to upload the previous links also. I will upload it today, and I don't know if you guys have access to it. So in your NPTEL itself, at corner you might be having problem solving session. So it will take you to some Excel sheet. In that Excel only I will upload all the presentations as well as the video link.
Okay, madam.
Any other doubt?
Hello, madam. I have
negative charge also repulse with each other.
What? Sorry.
Madam, hello, madam. Negative charges also repulse with each other.
Yeah,
positive
negative
also repulse with each other.
Yeah. Positive.
In this case, which charge?
In this case, actually, your negative charge are repelling each other. Somebody else was asking another question.
Yeah, hello, ma'am. I have some doubt regarding cement chemistry.
Okay.
Actually, I am working in one construction company. Generally, what we are using during concrete production, we are first we use what's aggregate, then final cement, then sand, then cement, then water. But in some case, we are using first we make cement paste. Means first we add cement, then water to make a slurry form, and then we put aggregate and this disaggregated final aggregate.
Okay.
Then is there any effect on If
Actually,
you if you if you if you first prepare cements already, then we put aggregate.
actually, the correct practice should be your aggregate should go first and then cement and water. That is the correct procedure,
Yes,
right?
yes,
If we add
yes,
your
yes.
cement slurry before itself, see, whenever cement will react with water, it will start hydrating itself, right? So if you are giving it opportunity to react first, hydrate first before adding your aggregates, then you won't get a good bond of your aggregates with your cement paste. So it will cause to your the bond problem will be there in that case. So that's why it's not preferred that you add cement. See, if you are adding aggregate cement together and mixing and then adding water, that is still fine. But if you add cement, water and then aggregates, then you are actually losing your good bond between your cement paste and aggregates, because your all water will start reacting with your cement. Your cement will start hydrating. Then you won't have an available water which will wet your aggregate and provide a good bond between aggregate and cement paste. Did I clear your doubt, or still you have any doubt?
Yes, yes, yes.
If you are not,
See,
yeah.
no, no, actually, I want to know about the chemical reaction with it, because if we add first water and cement, I think we don't have any unhydrated cement get leaks because of low strength.
Yeah,
Is
but
it true?
cement can hydrate in the longer term also. It's not the like instant hydration. I agree. You are telling like if I am adding cement paste first, the unhydrated cement will be very much less as compared to when you are adding it afterwards. But in the same way, if you are using your all water for your hydrating your cement, you won't have enough water left to make a bond or to wet your aggregate surface to make a bond between aggregate and your cement. So that will be a very weak link. Your
Okay, okay,
That's why.
okay. Thank you.
Any other doubt? Okay, if there are no more doubts, then we will close the class for today. Thank you all for joining, and if you guys have any doubt in between also, you can mail me on this my mail IDs. So thank you guys. You can log out.